Hello and welcome to the slope stability analysis session. Today we're going to talk about why do a 3D analysis. And my name is Murray Fredland and I'm excited today to talk to you about three-dimensional analysis. It's one of the types of analysis we've been focusing on recently, and we're excited to talk to you through why this is important. So as an overview, we're going to talk about why do a 3D analysis. What's the historical problem with a 2D analysis? What are typical differences between 2D and 3D slope stability analysis? What applications are affected? And what about back analysis? A lot of times geotech engineers will get into back analyzing a failed slope and determining material properties. And what's the proper way to do that? And we'll also talk about geometry effects and be able to draw some conclusions from this presentation here. So just to couch this presentation, industry has largely embraced a two-dimensional approach historically with respect to stability analysis. And we have accepted design factors of safety generally ranging between 1.3 and 1.5. So, but this typically brings up a lot of questions in doing the analysis. Well, what if I analyze in 3D? Is the factor of safety the same? If not, what's a typical difference? What is the advantage of doing a 3D analysis? And do I need a whole bunch of additional information to do a 3D analysis? And really, how do I interpret a design factor safety of 1.3 in the real world? And then what about back analysis? How do I perform it, and how should I be using material properties determined in a 2D back analysis moving forward? So we're going to attempt to answer some of these questions for you in today's presentation. So the problem fundamentally is that there is a difference between the calculations of factor of safety for failed slopes performed in a 2D as opposed to a 3D analysis. And the difference can be related to the geometry of the failed surface is one aspect. There are other aspects that cause a difference. And there's a common belief that a homogeneous slope with the same slip surface in 2D and 3D will give the same answer. In other words, if I extrude a 2D cross-section into 3D, shouldn't I get the same answer in a 3D analysis? And we'll talk through that. Should you get the same answer if you just extrude a 2D cross-section into 3D? Well, thanks to research performed by other researchers down in Brazil, this is Professor Gitarana, there's been lots of experimental studies in typical geometries and analyzing the slope stability in 2D and then in 3D. And in this particular study, we see an earth dam in a valley with typical parameters used to get a range of differences between a 2D and a 3D analysis. And in this case, on the graph, we can see our W to H ratio, and then on the left-hand side, you can see the difference between 2D and 3D factors of safety. And you can easily see that we can demonstrate, in this case, 4 to up to 16% difference in 2D versus 3D calculations just due to the geometry effects of a more complex earth structure. So if we go forward with this and talk about more retaining wall type of structures, either convex or concave, we can see that these type of structures, again, for the research done by Professor Gitarana, we can see that there is a common difference between 2D and 3D analysis that ranges between 36% higher in 3D and up to 72% higher in 3D. And so you can see quite a fair difference between 2D and 3D. And I guess we get a lot of questions about, well, isn't there just a standard difference between 2D and 3D analysis? And the answer is no. It's very dependent upon your geometry, your slip surface shape, whether there's anchors there, your loading conditions, your supports, a wide variety of things. And this just demonstrates the influence of simple cases of geometry on the factor of safety and demonstrating that you can have a fairly significant difference between 2D and 3D factors of safety. So it's important to note that when you're modeling a slope in 2 dimensions, you draw it into the computer as a 2D profile, and you draw a slip surface, you might have an anchor. It's important to note that really this converts to a 3-dimensional model. You're still modeling in 3D, only what happens is your model is extended in the 3rd dimension, and you're really modeling the slipping of a cylinder in 3 dimensions, with the ends, the vertical ends on the cylinder, having 0 friction. So that is why it is a little conservative in 2D analysis, is because you're not really considering the ends and the frictional resistance of the ends. And your anchor, of course, becomes a steel plate in 3D. Ideally, that's not the case. Anchors are point loads. So we scale it back and we artificially reduce the strength of anchors in a 2D analysis, but fundamentally, according to the theory, you're representing a plate in the 3rd dimension. And just to further reinforce that, if you take a 2D model and you extrude it out in 3D, and you can do this in our 3D software, and then you keep the slip shape the same, and you put 0 frictional resistance on the sides of the slip shape, you can duplicate the factor of safety from a 2D analysis to just demonstrate this concept that when you model and extrude models, the equivalent model has to be a cylinder that has 0 frictional resistance on the 2 vertical end sides. And so it's not a true representation. The problem with that is that it is rare to find in the real world a slip shape that looks like a cylinder in the 3rd dimension, and it has 0 frictional resistance on the side slope. So you've got a little bit of a disconnect with reality in terms of the shape of slip surface that you are modeling when you do a 2D slope stability analysis. However, it should be noted, there's been research done, well, what if we keep extruding wider and wider models and look for wider and wider slip surfaces in 3D? And research has been done in this area, and Jens, you can see the lines by his graph. He found that as you make a model wider and wider, and your slip shape becomes more approaches the plane strain conditions, your factor of safety drops back down to the 2D factor of safety. And so you can see that in the data points. That's demonstrated by Griffiths, Jens, and you can see that in our hybrid ellipsoid, where we have an ellipsoid that approaches more of a plane strain shape. As you make the model wider, we can demonstrate that effect with SV slope. The problem is that there is, in reality, small defects in the geometry or loading conditions, or any small defect quickly tend to collapse a surface desired shape back to an ellipsoid type of shape. Therefore, even though this is a perfectly theoretical condition where 3D drops to 2D, in reality you don't typically have that. You don't typically have, in reality, an infinite slope that is, the geometry is perfectly consistent in the 3rd dimension. Therefore, what you see with the crosses here is assuming ellipsoid slip shape, and you see that you have a minimum differential between 2D and 3D analysis that you hit, that is arguably maybe a little more realistic in terms of matching real world type of behaviors. Anyway, just a minor theoretical issue. Most cases are not perfectly extruded in real life, and so we can move on and model and push towards more theoretically close models to real world. So just as an example, here's a benchmark that was done in 1977. You have a water table, a weak layer, and so you have a composite slip shape and a factor safety of 1.223. And this typically is analyzed in 2D, and there's no questions asked or requested of this model. However, if you extrude this out to 3D and you assume an ellipsoidal slip shape, then what you find is that the solution normalizes at factor safety. It's about 8.7% higher and an aspect ratio of 5. And so you're searching for your perfect aspect ratio here in this case. And it is important that you are assuming an ellipsoidal slip shape in this case. So it's important to note that very often in slope stability, it's the one type of analysis that is almost always beneficial to do in 3D, because your slip shape is often ellipsoidal. It's a 3D slip shape, and if you're modeling it in 2D, you have an immediate assumption regarding the slip shape that does not usually match reality. So we have increase here that we can easily demonstrate here. So what can cause differences in a 3D analysis? Well, we have the influence of your slip surface shape. Moving from a cylinder to an ellipsoid or to a block model will all cause differences between 2D and 3D. Then there's topology. And what we've seen is small differences in topology can make a very big difference on the location of a potential slip surface. We've seen landslides that have been dictated really by topology, almost entirely. And you can therefore very easily predict the location of some landslides just strictly based on the topology variation, and which is nice in this world because we can have easy access to LiDAR data, satellite data, and all of that can give us very detailed topology data. Then there's the geostrata in the model that can give us differences. In other words, your geostrata may not be consistent in the third dimension. There may be differences. There may be weak layers that extend at strange angles, or fault planes that extend in strange directions in 3D, and we need to be able to account for that. Then there is your water table. Your water table may not be just consistent in 3D. It might have some variation. It might be seasonally affected by precipitation. There might be certain drainage paths that are dictated by material properties, and tables may follow more of a funnel flow type of arrangement. All of that can be accounted for in a 3D analysis, but not necessarily in a 2D analysis. Then you can have distributed or point loads in your model, which ideally should be represented as they are, as true distributed or point loads in 3D space. And lastly, you can also have anchors or support mechanisms for a slope that really are applied to a slope in a three-dimensional manner, and that anchors don't have to be perfect spacing in the third dimension. They might vary in their spacing. Micropiles might not be perfectly consistent in how they're installed. All of this can be potentially modeled in 3D and is difficult to model in 2D, and will yield a larger difference between a 2D and a 3D analysis. So I like this model. This was proposed by a Japanese researcher, and it really just illustrates a very simple topology, but one that is very difficult to actually analyze in 2D because you don't know ahead of time what direction the slip might take. And the topology really dictates that this should be ideally a 3D analysis, because it's hard to pick any particular slice through this model that doesn't have a 3D topology effect. So it's very easily demonstrated on simple analyses that these models are difficult to solve with a standard traditional 2D profile approach, and yet they're quite common. This is the typical slope that we would find in most municipal design and city planning, city layout, how we lay out our cities. So what are the typical differences between a 2D and a 3D analysis? And we get asked this a lot because, as mentioned, people think there should be a consistent difference between 2D and 3D. And the problem is, like the slide before highlighted, there are a lot of things that can affect the difference between 2D and 3D. So therefore, it's not one number. Part of learning to model in 3D is a discovery process where you learn in your particular application what are typical differences between 2D and 3D. And It can depend on a number of factors in your model. A 3D factor of safety will almost always be higher. And if you scour research literature, it was done by Gitarana in 2007, he noted differences between 15 and 50% in reviewing literature. Differences as high as 60% were encountered if you consider unsaturated soil mechanics. And that was a paper published in 2014. So we've always been told as geotech engineers, well, a 2D tool is conservative, and therefore we should use it because there's added safety in using a 2D tool. And even though that is true to an extent, we'll talk about that a little bit more. A 3D analysis provides a more theoretically sound analysis tool, particularly in the following areas like levee analysis, earth storage. If you're storing piles of earth, how steep you can store these piles of earth on properties depend on slope stability issues, and they're typically not plane strain. Tailings piles are complex. They become large, and the retaining structures are typically 3D in nature. The same with heap leach analysis, reinforced slopes and slope supports. All of these kinds of things have a very 3D effect that must be considered in the analysis. So we can talk a little bit about, sometimes we get the question, is a 3D analysis a better analysis, or is it more rigorous? Well, actually that's a fairly straightforward question to answer, in that we have approximately 20 plus years of research that clearly demonstrate that a 3D analysis is more rigorous. We typically haven't approached it because it's a little more work with the software historically, and it can be more complicated. Therefore, we simplify and do a 2D analysis. However, I would suggest that the software tools have come a long ways in recent times, and now the time difference between performing a 3D analysis as opposed to a 2D analysis is not that much different. It's really undisputed in academic circles that 3D factors of safety represents a better alignment with the real world, provided you build your model right and your slip surface geometry is accurate. And just some of the things that can also, a reminder, can affect your factor of safety. There's slip surface shape, topology, geostrata, water table, distributed point loads, and anchors. So this graph is very helpful in perhaps understanding the transition to a 3D analysis, because if we graph factor of safety on the left-hand axis, and then on the bottom axis we chart whether we're doing a 2D analysis or 3D, or we have actual knowledge of actual conditions, we can couch this in terms of how we are moving to 3D. First of all, we should note a few things. Once you go to 3D, you're moving closer to actual conditions, and therefore you will ideally get a closer alignment to real-world conditions. Secondly, we haven't changed the physics of failure, the definition of failure of 1.0 in our mathematical equations in moving to 3D. So the definition of failure of a factor of safety of 1.0 hasn't changed between 2D and 3D. But what you will typically note is that when you do a 2D analysis and you have a factor of safety of 1.3, and you do a 3D analysis of the same problem, your factor of safety will typically rise up some amount. And really, you should be aware of what your mentality is when you're doing a 2D analysis. What you're doing is you're analyzing it in 2D, and for example, you're saying to yourself that I have a known factor of safety of 1.3, and then really I have an unknown factor of safety that I don't know what it is, but I know that a 2D analysis is conservative. Therefore, I feel that there's added confidence in my factor of safety being conservative. Really what you're saying is that there's two factors of safety. There's the 2D factor of safety, and then there's the difference between 2D and 3D. And I don't know what the difference is, but I do know the 2D factor of safety. Well, really what we're talking about now is that we can know the difference that we didn't know all these years, and it gives us a better tool in our toolbox to make better professional judgment decisions. So we can know both the difference between 2D and 3D and the 2D factor safety. And as a matter of practice, we continue to recommend that our clients run both 2D and 3D analysis to start understanding the differences between 2D and 3D analysis and why they're getting those differences and what's causing them. What are the physics that are driving those differences? And scale in the 3D effects a little at a time to understand those differences. So this also relates to a related question in that, we'll just go to the next slide here. We have to understand that existing limits of 1.3 and 1.5 have been developed in the context of a 2D analysis. And it's not right to necessarily just apply them directly to a 3D analysis. We recommend running both 2D and 3D and understanding really historically what you've been doing up till now for a certain class of problems. For example, if you reanalyze existing 2D problems in 3D and you find that really you've been realistically working with a factor of safety of 1.45 when you thought you were designing for 1.3, then that aids in your professional assessment of what factor of safety, now that you have a more accurate calculation of factor safety, should be used in the analysis going forward. So professional judgment is still required in the interpretation of model results. Basically, you have a better model now. You still need to use professional judgment on how you interpret the results. I'd like to talk a little bit about back analysis because it's an important aspect that's often misunderstood in the geotechnical community. We typically get a failure, when we get a failure, we typically go in and we do a two-dimensional back analysis. And we back out material strengths that give us a factor of safety of 1.0. And then we feel confident that we've determined those material strengths, and we often use those to design our fixing of the slope or the design of another part of the slope. You are in this process, you will overestimate the strength of the slope is the danger of this, because material, since moving to 3D analysis produces a higher factor of safety, when you do a back analysis with a 2D product, a 2D software tool, you are actually overestimating the strength of your materials involved in your slope. Therefore, you will yield a weakened condition if you use those parameters going forward. You should, just a further note on back analysis, you should always use a three-dimensional tool when doing a back analysis of a slope, such that you properly determine the material strengths that you're actually dealing with. So, just another look at geometry effects. More research done by Gitarana related to convex and concave slopes, and we can see from this that there is effects of both your location and your factor of safety related to strictly geometry effects, and those can be easily quantified by doing simple analysis problems. So some of the conclusions we can draw from this is we know that 3D limit equilibrium analysis is theoretically more rigorous than a 2D analysis. We can summarize that a 3D factor safety will typically be higher than a 2D factor safety, and an extrusion of a 2D model will not necessarily yield the same factor of safety as a 2D analysis, especially if you change your slip shape and go to an ellipsoidal slip shape. So you're changing your slip shape, and that will yield a different factor of safety calculation. Differences between 2D and 3D analysis are very much dependent upon slip surface shape, topology, geostrata, water table, distribution in the third dimension, distributed point loads, anchors, micropiles, geomembrane, placement in 3D, and all of that can have an effect on the 2D and 3D aspects of your analysis. And very importantly, material properties determined in a 2D back analysis shouldn't be subsequently applied to a forward analysis. And you should really be doing a three-dimensional analysis for all back analysis studies. So just as a note. So overall, 3D analysis allows for a more rigorous calculation of the true factor of safety. So I'd like to thank you for your time, and we will go through just a very brief demonstration of how to set up 3D models and give you a brief overview of how to build 3D models and how to access the software.